The transformer is connected to supply voltage, but the secondary is left open. That means secondary is not connected to load. This is the case when the transformer is on no load condition. V1 is the supply voltage, I0 is the no load current, E1 is the primary back EMF, N1 is the primary number of turns, N2 is the secondary number of turns, E2 is the secondary back EMF, P2 is the secondary terminal voltage, I is the flux in the transformer core. And this is the vector diagram when the transformer is on no load condition. These are the supply voltage V1 and flux in the transformer core, the magnetizing current IM, primary back EMF, secondary back EMF, and the secondary terminal voltage equals to secondary back EMF. E2 equals to V2 as there is no load connected on the transformer. V1 leads the flux by 90 degree and back EMF E1 is in phase opposition to terminal voltage V1. So the same E1 can also be mentioned on the primary side with minus sign minus E1. These are the terms corresponding to primary side. These are the terms corresponding to core. These are the terms corresponding to secondary side. So this is the basic vector diagram of transformer. The equivalent circuit. When the transformer is not connected to load, these two are primary windings and secondary windings. This is the transformer core and there is no load connected on the secondary side, and the primary is connected to supply voltage V1. As there is no load on the secondary side, the primary will draw only no load current I0. This no load current I0 can be segregated into working component IW and magnetizing component IM. The corresponding impedances are R0 and X0. These are connected in parallel with reference to primary circuit. So this is no load current I0 and this is working current IW and this is magnetizing current IM. The magnetizing current IM and the flux in the core both are in phase, and this no load current I0 is vector sum of IW and IM. This is actually very small compared to full load current. This is only 2 to 5% of full load current. And phi naught is the phase angle between supply voltage and no load current. The no load current is I0, which is segregated into IW and I mu. IW is cos phi naught, I mu is, or I magnetizing current is I0 into sin phi naught. This is derived from this triangle. This is current I0, this is working component IW, and this is magnetizing component IM. So here we are considering this theta. From this theta value, I0 cos phi naught will be IW, I0 sin phi naught will be I magnetizing current. So this can also be written in this form: I0 square equals to IW square plus IM square. From this equivalent circuit, this IW and I mu can be written in this form: IW working component with reference to resistance, I mu or I magnetizing current with reference to X0. The supply voltage is common. As these two R0 and X0 connected in parallel, the corresponding current in these two elements is supply voltage divided by that corresponding element. So from these discussions, a total power loss P0 is calculated. P0 equals to supply voltage V1 and working component I0 cos phi naught. This is working component. So the no load power loss of the transformer P0 equals to V1 into IW. IW equals to I0 into cos phi naught. So this is only gives total iron loss of the transformer under no load condition. No load current, magnetizing current and working current. But on the larger scale, the no load current is only 2 to 5% of total full load current. If you compare R0 and X0 values, R0 value is very high compared to X naught value. So the angle between supply voltage V1 and no load current I naught, the angle is phi naught. The phi naught, it can vary from 70 to 80 degree, or it can be very near to 90 degree also. So the no load current is almost equal to magnetizing current Im, which is almost in phase with the magnetizing current or flux in the transformer core. So as the angle is very high, the power factor will be very low. This is a waveform representation. This is supply voltage V1 and this is primary back EMF minus E1. These two are in phase. These two will be in phase. And this is flux I and magnetizing current Im. These two are in phase. That means these two will cross 0 at the same time. Magnitude may be different, V2 and E2. These two are in phase. So this is waveform representation of parameters of the transformer. Flux variation and effect on the core. kVA is directly proportional to Vmax AN into F. The kVA is directly proportional to frequency. And the relation between V maximum and frequency is inversely proportional, as these two terms are on the same side of equal to magnetizing current Im equals to V1 by X naught. X naught will be 2 pi FL. So the magnetizing current is inversely proportional to frequency. As the frequency decreases, magnetizing current will increase. This is the graph of frequency and magnetizing current and flux density Bm. This is the 50 Hz. Corresponding magnetizing current is this and the corresponding flux density is Bm. As the frequency decreases, this is new frequency 20 Hz and the corresponding magnetizing current. As the relation between magnetizing current and frequency, as the frequency decreases, magnetizing current will increase. So the corresponding Bm will be 2 times the Bm. So this is the break-even point and this is saturation point. As the flux decreases, magnetizing current will increase. The core will go into very deep saturation. So this is saturation point. So the relation between V maximum and frequency and magnetizing current, this one we have to remember. So as the frequency decreases, V maximum increases. As the frequency decreases, I magnetizing current also increases. V maximum depends upon nature of the material. This is CRGO material. For example, if our transformer is operating at 50 Hz supply, if we decrease the frequency from 50 Hz to 5 Hz, then in this case, as the frequency decreases, magnetizing current Im increases, core goes into very deep saturation. The no load current I0 increases. As the windings are having very low resistance, it will draw higher currents from the supply voltage. So the transformer windings may get burned or it may smoke. So these are the important points with reference to when transformer is on no load condition. So from these points, you have to remember these vector diagrams, waveforms, equivalent circuit, and these formulas. And finally, from no load equivalent circuit, we calculate no load power loss, that is iron loss.